Welcome to Khetztutorials, and in this video I'll be talking about compound angles. So this is a continuation of where we left off. It's basically just the next topic under trigonometry, and as I said, we're going to be talking about compound angles, right? So these compound angles basically describe the adding or addition or subtraction of angles. Basically, that is what they describe. And before we start, please note, and be nota bene, please note that if you have cosine of, let's say, a plus or minus b, it is not equals to cosine of a plus or minus cosine b. So you don't actually distribute this cosine to each of the angles which are found in the argument here. And the same applies for sine. If you have sine of a plus or minus b, it is not equals to the distribution of that function to each of the angles, right? So you actually have proven formulas for each of the above, which I just showed. So we have proven formulas for this part, we have proven formulas for this part. And the formulas are as follows. So these are the compound angle formulas, formulae, if you like, just write formulas. So we have cosine of A subtract B equals to cosine of A cosine of B plus sine of A sine of B. So this is the first formula which we have with respect to cosine. And the next formula says A plus B, cosine of A plus B will give you, so let's just write this a bit closer. These are not two separate things, this is just one thing. Cosine of A plus B will be equals to cosine of A cosine of B subtract sine A sine B. You'll notice that you have a sign change. If you have cosine of A subtract B, it results in cosine A cosine B plus, right? And here you have the opposite. If you have a plus sign, it results in a negative. So here's the first thing to note for cosine in your compound angle formulas. There is a sign change, right? Going to move on to the ones which are associated with sine, and they say sine A plus B is equals to sine A cosine of B plus cosine of A sine of B. And the next one says sine, if you have sine of A subtract B, then you have sine A cosine B subtract cosine A sine B. Now here you'll notice that there isn't any sign change. If you have so there isn't any sign change, that is. So if you have a positive, you're going to have a positive in the output. If you have a positive here, a negative there, you're going to have a negative over there. So for sine, there is no sign change. So no sign change. And you'll notice that for sine, you have sine cosine, cosine sine, sine cosine, cosine sine, instead of having this cosine, cosine, and sine, sine. So they actually differ in that one of them has sine of one angle and the cosine of the other angle added to the cosine of the first angle multiplied by the cosine of the sine of the other angle. And here you have the cosine of one angle multiplied by the cosine of the other angle, and here you have the sine, subtract the sine of that and that. So here, two things that you should note: the formulas themselves are different for cosine and sine, and secondly, For cosine, you have a sign change, and for sine, you don't have a sign change. So that's something which you should note as you study these. And now we can't just say this is actually true without trying to substantiate or to actually solve or prove that these formulas are true. But before we actually prove that the formulas are true, I just want to put out an exception over here. As I was saying, there are exceptions. So basically, the point I'm trying to make now is don't use compound angles if you can use basically reduction formulas. So reduction formulas, and if you remember, reduction formulas are what we discussed in our previous video. And for example, if you have sine of 90 degrees subtract theta, don't split this into sine 90 degrees cosine of theta subtract cosine of 90. This is too long, and it's quite unnecessary for you, let's say in a test situation. Without even using the compound angles, you know that the answer to this is cosine of theta, right? So if you can basically simplify something just using the reduction formula, please go ahead and do so. But if you see that you can't, or if you see that splitting your trig function into something like this would be helpful for you, then do that. But if not, then don't. So now we're basically going to move on to the proofs of these formulas. And to start with, we are just going to draw a circle. And that circle is going to have a radius of 1. So the circle is going to have a radius of 1 over here. So basically going to draw a circle. Let's just drag it and put it there. And now our circle is going to have a radius of 1. And let's just assume that the center is somewhere there. Okay. Okay, and we also have axes which show the y. And the x-axis, which is going to look something like that. Okay, so this is the x-axis. This is the y-axis. Here you have your origin, which is basically 0. And we said that we are drawing a circle with a radius of 1. So that is 1, and that is 1. The length of that is 1, and the length of that is 1. And we're also going to draw a line from one point to the other. Let's draw this. So this is the proof of each of the compound angle formulas. So let's say this point, at this point you have r. And remember that your x and y coordinates can be given by r cosine of theta. And in this case, we're basically going to be working with A and B. So this is A, the angle from there to there, and this is B, which is the smaller angle, which is just from the x-axis to the first line. We're going to call that angle B, right? So the x is associated with something like this, and the y is associated with r of sine theta. So now that we have our r as 1, you don't necessarily have to write it. You can just say cosine of A for that point and sine of A. Now at this other point that we have on that side, you can say cosine of B and your sine of B. So those are the angles which are associated with each of the lines and each of the points. So that is the coordinate for that point over there. And this is the coordinate for that point over there. We can now call this line D to denote the distance from one point to the other. And we can start our analysis of this diagram. Now, if you know the distance formula from previous grades, or let's say grade 11 or whatever grade you know the distance formula from, it basically says that d is equal to the square root of, then you're going to subtract your x1, subtract x2, and then you're going to square that, add it to y1, subtract y2, then you're going to square that too. So which means that your d squared is equal to, you basically remove the square root sign on the other side as well. So in our case, if we take this side to be x1, y1, this side to be x2, y2, we're basically going to have d squared equals to cosine of a subtract cosine of b squared, then we're going to add that to sine of a squared, sine of a, subtract sine of b, then we're going to square that. Let's remove this so we have more space. So you have that, and the result of this is basically just applying your algebra. You're going to have cosine squared, then you're going to have negative 2 cosine of a cosine b, and finally you're going to have the square of the last one. So the same thing applies to this other bracket over there. So you're just basically going to have sine squared a, subtract 2, and then those 2 multiplied, then you're going to square the last one as well. So now from this, you'll see that you have cosine squared a, and you have your sine squared a. Now here's another interesting formula which you should know. If you have the same angle and you have your cosine squared of that angle and the sine of that angle, if you add these two, they should add up to 1. So this is an identity. I'm going to look at identity in more detail in the next video or in the coming videos, but this is what you have to know for now. So if you add this and that, you should get 1. If you add this and that, you should also get 1. So basically we have 1 plus 1, which is 2 currently. So you have 2 as the result. Subtract 2 sine A, sine B, then you also have minus 2 cosine of A, cosine of B. Now that we have that, you take out this common factor of negative 2, if you like, just to simplify your equation. So you're going to take that negative 2 out because it's common there and there. And therefore, you're going to just have sine A, sine B in the brackets, and your cosine A and cosine B. So this is the first part. This is the first formula after using this distance formula. Now for the same distance, we can use the cosine rule. So this is another thing which I expect you to know, but we will also revise the cosine rule at a later stage. Cosine rule. So we're going to use the cosine rule as well to solve for d squared. So d squared is equals to OP. If you look at the diagram, if you look at the diagram, OP is basically from 0 to P, so OP from there to there. So your d squared is going to be OP squared plus OR squared, which is from the origin to the point R squared, and you're going to have subtract 2 multiplied by OP, and then that multiplied by your OR, and multiply that by cosine of A, subtract B, right, which is the angle formed between A and B, so A subtract B. And that is your cosine rule. So the reason for this formula of you is basically the cosine rule, right? And now that we have that, you'll notice that the length of OP and OR are each 1 because both of them are radiuses, and we said that the radius is equals to, so the radius basically equals to 1. So adding those two will just give us 2, and here we also have 1 and 1. Then here we have cosine of A subtract B. Then after doing the math here, basically just have to subtract 2 cosine of A subtract B. Right? So d squared is equals to the first formula and this second formula over here. So you can basically equate 1 and 2. So equating 1 and 2 or 2 and 1 doesn't really matter the order which you use. They're basically equal because both of them are equal to d squared. So doing this now, we're basically going to have 2 subtract 2 cosine of A subtract B is equals to this over here, right? Which is negative. So let's look at the full formula so we don't miss anything. It's basically 2 subtract 2 multiplied by sine A sine B plus cosine of A cosine of B. Now that we have that, you can basically just do some quick math. It's a simple math. Just take this 2. If you take this 2 to that side, it will basically cancel out with this 2 over here, which means we just have negative 2 cosine A subtract B is equal to negative 2 sine A sine B plus cosine of A cosine of B. Now you can divide both sides by negative 2, and that will lead us to the following formula, which says cosine of A subtract B after dividing both sides by negative 2. Here we subtracted 2 on both sides. So after dividing both sides by 2, negative 2, we're basically going to have cosine of A subtract B is equals to sine A sine B plus cosine of A cosine of B. And lo and behold, we basically just proved that cosine of A subtract B is equal to cosine of A cosine of B plus sine of A sine of B, which is basically the original formula which we had when we were discussing our compound angles in the first place, or when we introduced the compound angles. It basically introduced these as being true to us, even though we didn't have proof. So it basically just proved that the compound angles or the compound formulas which we just wrote down here are actually true. So from this information over here and from this proof, you've actually seen that this actually works. So that is basically one of them out of actually 4 of the compound angles. So we can actually use this to prove the others. So let's do that quickly. So the second proof would be so we're going to use this to prove that cosine of A plus B is equals to cosine A cosine proof of this. So cosine of A cosine of B subtract sine A sine B, and this is how we're basically going to do that. So on the left hand side we have cosine of A plus B, and previously we proved that cosine of A subtract B is equal to that. We just proved that not so long ago. Now we can manipulate this formula to look like this formula over there. And to do that, we're basically just going to say A subtract minus B. And it basically kind of looks the same. And therefore, this, since it's proven that A subtract another angle is equal to this, we can just basically do the same thing over here and say we have cosine of A, cosine, in this case we have negative B because negative B is the second angle. Then we're going to have the negative, which is what follows, so it's basically positive, which is what follows in this formula. Then we're going to have sine A and then sine of negative B. Now, if we go back to our reduction formulas, or if we go back to look at our quadrants, you'll notice that if we go in the cost diagram, if you go in the negative direction, you find yourself in this quadrant where cosine is positive, which means this is cosine A, cosine of positive B, right? And only cosine is positive in that quadrant, which means we have negative sine over there. And we're going to take that negative outside here because it multiplies everything, and the result would be this. So then we can actually conclude that, and this is equal to the right hand side, we can actually conclude that cosine of A plus B is equal to cosine of A, cosine of B, subtract sine A, sine B. We just proved that by manipulating this original formula of A subtract another angle, which we just proved previously. We're now going to move on to do another proof. So we're going to base all of our proofs on what we basically proved so far. And now we just proved that, or previously we proved that cosine of A subtract B, right, is equal to cosine of A, cosine of B, plus sine of A, sine of B. Now we're going to use this to prove that, sine A plus B is equal to sine A, cosine of B, plus cosine of A, sine of B. That is what we're going to prove next. And how can we actually do that? So if you remember, we have co-ratios which say that if you have your cosine of 90 degrees subtract a certain angle, let's say theta, then you basically have sine of that angle. So now in our case, on the left hand side, we have this, and that is the same as having cosine of 90 degrees subtract that same angle. Now that we have 90 degrees subtract that same angle, we can basically come and say that we have, so we can split this and say that we want to make this look like what we've already proven up here. So we can actually split this and say we have cosine of, then we're going to divide the angles inside into 90 degrees, subtract A, then we're going to leave the negative B on its own, right? And now we're basically going to say we have cosine of 90 degrees subtract A multiplied by the cosine of B, because of this that we proved at the top over here. So you're just applying what we proved at the top. Now that we have something similar to it, we're going to have this, then it's going to be added to sine of 90 degrees subtract A multiplied by sine of B. Now that we have that, which is quite similar to us, we are just going to do the co-ratios once again, and the result of that would be sine of A cosine of B. Then we're going to have cosine of A sine of B as the result of this. And therefore, we have ultimately proven that the left-hand side is equals to the right-hand side. So always, when you prove, you deal with one side and actually prove that that one side is equals to the other side. So in our case, we started with the left-hand side and we proved that the left-hand side is actually equals to the right-hand side. I'm going to move along to another proof. So this is the last one. So basically first proved this, and after that we proved cosine of A plus B, right? And then after that we just proved that sine of A plus B is equal to that. So we're only left with one proof. Okay, only left with one proof, and that will be it for this particular video. So let's do that last proof that we have. You're going to use the same cosine. A subtract b is equals to cosine of a, cosine of b, right, plus sine of a, sine of b, to prove that sine of a subtract b is equals to sine of a, cosine of b subtract cosine of a, and sine of b. So that's what we want to prove right now, and we're using the same statement which we proved previously. So what can we do in this case? We are basically going to do a similar thing and say that cosine, so it's similar to what we just did previously just now. So we're going to say left hand side, we have your cosine 90 degrees subtract a subtract b, which is equivalent to this sine of a subtract b. These two are equivalent. And from this point, we can split this angle and say that we have cosine of 90 degrees subtract a. Then we have that added to this, right? And now that we have that, we can just come and divide this into two parts. You can divide this into two parts and say that we have the cosine of 90 degrees subtract a, and the cosine of, so this is equal to cosine of 90 degrees subtract a and the cosine of b. Then you have your negative sine 90 degrees subtract a multiplied by sine of b. I'm just running out of space, so just make sure you have that multiplying each other. And from that, you're basically gonna have a result of sine a, and you're gonna have your cosine of b, and it's gonna subtract cosine of a multiply sine of b, and that is equals to our right hand side. So we've ultimately proven that your sine a subtract b is equals to that, and we are basically done with the proofs that we're actually interested in. And that is basically all that I had to discuss in this video. That is basically all. And so we discussed compound angles, and I also showed how to prove each of the formulas which we said were true, and I hope you were following. If anything still isn't clear, please leave a comment. And if you like the video, just go ahead and give it a thumbs up. If you haven't subscribed, please subscribe, and I will see you guys in the next video.